So we're going to have a look at a lot of things connected with entropy and the arrow of time in the universe. I've titled it The Boltzmann Brain and Maxwell's Demon, and we'll talk a bit about what both of those are shortly. Okay. When we look at the laws of physics, it's typically the dynamics of the system plus initial conditions, and that will give us the evolution of the system. So if I know at some point, it actually doesn't have to be an initial condition. If I actually know condition anywhere along the evolution of my dynamical system, if I've got the laws of evolution, I can predict what happens in the future with certainty. I can wind the clock back and see what the initial conditions were. But within the deep down laws of physics, there's no intrinsic arrow of time that we can see. There's some hints that there might be, but fundamentally when you record particles bouncing off each other, you play the tape back, the same laws of physics play out. So there's no intrinsic arrow of time in the deep laws of physics. Where it emerges, there's one very significant law that it emerges. Anyone know what law that the arrow of time really emerges in? Yeah. The increase of entropy, which is one of the thermodynamic laws. You know which one? So almost two. So the second law of thermodynamics is that entropy always increases. So the arrow of time is clearly in the laws of thermodynamics. If something is ordered at one point in time, you would expect it to be in a more disordered state at a later point in time. Okay. The interesting thing is, though, that that's just as a result of this statistical improbability of having ordered systems. And if you took this same ordered setup, because the laws are symmetrical in time, you would expect it to be more disordered in the past. So from the law of entropy, the deviations from a disordered system would be purely statistical, and by chance you would get something really ordered. And then you would expect that in the past, that if you ran the clock back, you would expect to see it more disordered. And that's how Boltzmann thought the initial conditions actually happened. If you have an infinitely long timeline, just by chance, you would get a really ordered state that then became more disordered over time, and you would get the evolution of the universe. So these laws of entropy came end of the 19th century when they were studying about heat and about reversibility, ultimately how much work you could get out of this system. And it was very much defined by the reversibility of the system. So the first law of thermodynamics is basically conservation of energy. Second law of thermodynamics is that things tend to approach equilibrium, become more disordered. So heat flows from hot things to cold things, not the other way around. It's a very clear, observed arrow of time. And the third law of thermodynamics is that there's an absolute zero temperature. So if everything is at 0 degrees Kelvin, a crystalline structure, there's a maximum level of order, and you can't actually ever get there because of the second law. So you would have to make something else more disordered to get some other place, to have some kind of heat pump. So the actual most ordered state of matter is just out of reach at 0 degrees. Now this applies to much more than just temperature. So we see evolution from any ordered system statistically to a more disordered system. So for instance, if I had some air freshener, if I spray some in one corner of the room, then you would expect those particles, just with random interactions with air in the room, to spread out, and you'd be able to smell the air freshener all over the room. But it'd be really unexpected for a room full of air freshener for that air freshener to collect in one corner of the room. Now, the reason for this is very much connected with information. So we're going to think about signals and to look at a definition of information. So a bit is the simplest, smallest block of information you can get, either a yes-no answer to a question. So if I have my 3 yes-no questions, so it's a bit like a card trick. Do you want the left side or the right side? So at the first choice, you've got 1 bit. So these are all the ones in the first, and these are all the zeros. And then you've got a second choice, splits it again. So there'll be 4 options. Third choice gives you 8 options. So the information can be stored in a system with a number of states available. So if there's 8 possible states, the number of bits of information that will store, you work out for log to the base 2 of the number of states. So here we've got log to the base 2 of 8 gives us 3. So 3 bits of information in a system that has 8 possible states. Now going on to thermodynamics. So this is one of the key founders of thermodynamics, Ludwig Boltzmann. You can see his equation for entropy is very similar to that equation for the amount of information that a system can store. S is entropy. It looks very much the amount of information, or the number of bits that you would require to store information. And then we've got a constant, and we've got log of the number of states. Okay, so the log of the number of states gives us this term about entropy, so that in terms of information and a physical system, entropy is analogous to the amount of information needed to encode that system in some way. It doesn't matter what base this log is, it's just a constant. So you could transform this into bits. In the equations for entropy, I think it's base 10. It's related to Boltzmann's constant, but structurally it's the same equation. So it's the amount of information to describe that system is related to the number of possible states in that system. Okay, now the connection with disorder. So if we define entropy as a measurement of disorder rather than the amount of information to describe something, the entropy of a system is defined proportional to the natural log of the number of microstates corresponding to the observed macrostate. So here's the equation we just had. So it came to this equation from a slightly different direction than the framing of information, but it means the same thing. And basically it means that there are a lot less ways for a system to be really ordered. For instance, the air freshener in one corner of a room, there's very few ways for that to be organized. But if you spread all the particles all over the room, there are vastly more ways that you can arrange those to get the same macro state. So if the macro state is that you can smell the air freshener everywhere, there are many more times the states that look like that on the large scale that look at all in one corner. And with a random walk through there, it will move through those states more probably. There's a very small chance that it will find that configuration with them all in the corner, but because there are vastly more states that are disordered than are ordered, you would expect an ordered system to evolve towards a disordered system. So with statistical mechanics, there should probably be a health warning. So here's a great start to one of the books on statistical mechanics. Oops. Ludwig Boltzmann, he spent much of his life studying statistical mechanics, died in 1906 by his own hand. Paul Einfrest, carrying on the work, died similarly in 1933. It's your turn to study statistical mechanics. But it's not necessarily depressing thinking everything's just chance. We have scientists who were very different in their outlook. So this is Maxwell. He was very significant in terms of statistical mechanics too. And he thought about the possibility of creating order in a system. So he created this thought experiment. So imagine you've got, say, a gas spread out in 2 boxes. All the particles are moving at different speeds. So you've got some here, the black ones, let's say, are moving faster than the white ones. And then if you could take all the black ones and put them in one side of the box and all the white ones on the other side of the box, then you would have a high temperature gas on one side and a low temperature gas on the other. And he imagined a demon who could open and close a little shutter door. If a particle came up to the window and it was a high energy particle, he would let it through one way. If it was a low energy particle, he would let it through the other way. And he would sort the particles out without any additional work on the system, using the kinetic energy of the particles. And you would then have a system with a hot area and a cold area that could be used to do work. And it wasn't until the ideas of information and the connection of information with entropy that the solution to this puzzle was worked out. And if this daemon is a physical thing, you work out that the amount of information processing that would have to happen in a system that would record, you have an information change in the system, the sorting, And that will always equal an increase in entropy that relates to the decrease in the entropy of the overall system. So there's no loopholes to be able to create this low ordered state by any physical system. Okay, so now we have the big cosmological mystery. Okay, so we look back in time. We have our time scale going back as we look out further and further into the universe, and we see an evolution of structures, and we go right back to the Big Bang, and we see everything as a uniform. The cosmic microwave background is uniform. It's all thermally equalized. So it looks like it's in a state of matter that is perfectly disordered. It's a maximum entropy. And the mystery is, how do you get from a system that is thermodynamically really smooth, everything's spread out, so constant temperature everywhere you look, to a system which has very ordered systems like ourselves? Okay, so there's been a clear evolution of structure and ordered structure. So thermodynamically, we've got really hot spots and cold background. Okay, our apparent evolution of the universe seems to have gone the opposite way to the only law that we know that has an arrow of time in it in terms of evolving towards more disorder. Okay, anyone know what the missing bit that I've left out of the picture so far is? Seb? Don't know? Anyone else? Okay, there's also something else that's going on here. There's an evolution of gravitational systems. Now, when you look at gravity, it changes things because it's always attractive. For a gravitational system, you would expect it to evolve to things being more and more dense. Okay, if you've got something all spread out and there's a very slight density imbalance just by chance, you would expect the slightly higher part of mass to start attracting, and it will have a kind of runaway effect. Okay, so you effectively have an evolution to a more disordered state, but only now the disordered state is defined in terms of gravity. So something that's very ordered gravitationally is something that's really smooth. So the solution is we look at this smooth background radiation. That's not actually disordered compared to now. It's actually incredibly ordered because of gravity. You would expect gravity with things to end up in clumps, but because it's all really smooth and finely balanced, the order is there to start with. And then as you have this evolution in terms of the gravitational systems condensing, you have this evolution of structure and the creation of these hotspots in the background of the cold space so that we can now do thermodynamic work. So you have gravity effectively pumps order into the thermodynamic systems and enables complex structures to evolve in the universe. Okay, and that's effectively where the order that we see in the universe comes from. It comes from a really ordered state at the beginning, so it doesn't contradict the second law of thermodynamics. So everything's in alignment. So we've got the cosmological arrow evolves toward more disorder. The expansion of the universe, that lines up, and our evolution sits in that. The evolution of complex structures are basically using up the order that was in the initial creation of the universe to do work, to create ordered systems. So when we're eating something, we're taking in ordered energy that was ordered by the heat of the sun on Earth. So that you have the light of the sun creating ordered chemical structures that we're eating to then do work in our bodies. If you go back a step further and ask, where did the order in the sun come from? It came from the collapse of that ordered material in the beginning to make it this hotspot in the sky. So ultimately, any ordered bit of energy that we are using to do some work, whether that's food or radiate from the sun or even any chemical energy, that has its ultimate source in the gravitational order of the start of the universe. Okay, but now the mystery is, so the entropy must go to zero at the beginning of the universe, just like everything was on top of each other. If we wind the clock back, everything's getting closer and closer together. And as we go back in time, it's getting more and more ordered. So the mystery is, how do you get a state which is at perfect order at zero distance from each other right at the start? Okay, so we've explained everything else, but by assuming the most improbable thing that you could possibly imagine to exist, okay, which is a perfectly ordered, infinitely dense, infinitely wide system. So it's not like the Big Bang is a point. You have to imagine if the universe goes forever, it's just everything on top of each other, but perfectly ordered. Okay, so we now have the start of the Big Bang is the ultimate mystery. Now, when you get to that point, that's the edge of physics where we've got lots of ideas that people come up with, but effectively the trouble is we move from science into metaphysics very quickly when we get to that point. We move beyond the edge of our experiments and we move into the ultimate mysteries of where everything comes from, the Big Bang. And we will get into some of that. These are the evolutions of structures. There's some interesting stuff on similarity between information structures on really large scales and really small scales. So this is really large scales on galaxies. This is the size of a neuron. This is a single-celled organism. This is a nebula. But ultimately, all that order came from some kind of improbability drive right at the start. That if we're looking for an explanation of why anything exists, it's that Big Bang state that is the ultimate mystery. I'm going to post the next lesson as a YouTube video. I did a talk for one of the Avni lectures on end of Moore's law and the beginning of the universe, an exploration of singularities. So the talk will give a bit of a briefer overview of the evolution of the universe in terms of entropy, but also look at the computational power of the universe. Think things don't just happen by chance. You have systems that can compute, and there's very interesting work being done in terms of quantum computing and in terms of things like black hole computers and the ultimate limits, the physical limits of computing in the universe. So in the talk, we'll take a bit of the look at this evolution of order extended to technological system. And then I would highly recommend this book, or even looking up Seth Lloyd on YouTube. He is a quantum physicist, but he works on quantum computing. So he very much sits between these cosmological mysteries and engineering, actually building. He calls himself, he's a quantum mechanic. He literally builds computing systems. But this book is a fascinating read, and also his paper on the computational power of quantum systems and computing in the universe. There's a few papers I can post links on the classroom. But on Wednesday, I'm out at the CanSat competition, so the lesson will effectively be that talk on YouTube. Okay, any questions?
Sir?
Yes, Oliver.
I missed last lesson. Would it be possible to see the recording for that?
Yes, I think I've posted it on the classroom already.
All right, thank you.
So the last one was just an overview of the evidence for the Big Bang. So it was a kind of condensed packet of the A-level cosmology course, just looking at how we got the distance ladder and how we figured out that the universe was still expanding and therefore it had a beginning, and all the evidence for evolved structures in the universe. As you looked further out into the universe, you could see things were different in the past. So what had been the accepted idea that the universe was eternal then changed. For instance, Boltzmann believed in an eternal universe. Up until the Big Bang was accepted, the predominant worldview was that the universe was eternal, and therefore the evolved structures in it were, or any order in it would have been a statistical outcome. If you have an infinite universe lasting forever, at some point, any degree of order that you could imagine would happen, even if that's really unlikely. But then with the proof for the Big Bang, we can see that the initial state was really ordered. And now that's the big question that is on the edge of physics and into metaphysics. Okay, any questions?
Actually, how do they have a time scale?
Pardon?
How do they have a time scale?
Lord Kelvin came up with the idea at the first, just in terms of thermodynamics. If you look at the second law of thermodynamics and you project it forward, then ultimately everything must reach equilibrium at some point. And in terms of if you include gravity in that, then that would also be the case. So in terms of gravity, the maximal entropy is when everything's in black holes and the background is completely spread out and just keeps on spreading. forever, and if there's no temperature differential, there's no possibility to do any work. How that plays out, there's some questions about how that plays out now with when you combine quantum mechanics with general relativity, the idea that black holes aren't so black and what actually happens. There are different ideas about what could ultimately happen beyond that. And we'll have a look at some of those hopefully next week.
Thank you.
Okay, great. And as before, any questions or comments, stick them in the classroom. Okay.
Thanks, sir. Have a good weekend.
Thanks, sir.
Have a good weekend.
Thanks, sir.
Good week.
You too.